We're starting right now.
Nothing, Santos. You're ready.
Literally just started.
All
Yeah, I
right.
just popped out of the shower. Long day.
So what we have here is we have wall section.
I'm opening a root beer. I apologize in advance.
My gosh, how dare you? So this is a wall section, but it's not like it's not going to be your typical wall section. So normally when you have a wall section, I forgot to set up my line thicknesses. So normally when you have a wall section, it's like in your studio classes, you have a, you have a wall that's like here, and then you have like a roof or something. And you have like the floor. Right? And then here's your little human being right here. So this is like this is a vertical cut almost. So if you like so you have a house right here, Blamio. You're cutting through here. And this is, you're getting a vertical cut right here. But here, you're actually taking a horizontal cut so that you will be able to see the studs right here in between the insulation, or more like the insulation in between the studs. So instead of this vertical wall section, you're taking a horizontal wall section. You're cutting through the wall this way. So you're still going to see the same elements. You're just going to be able to see studs that are dispersed within the wall. So that's just the basic overview of what you're looking at right here. All right. So we have 7 different materials right here. We have face brick, vapor barrier, insulation board, plywood, metal studs, batt insulation, and gypsum board. So if we look here, you can see the brick. This is the brick right here. You zoom in a little bit, you can see that the vapor barrier is like this boy right here. 1.5 inch polystyrene board is this one. 1/2 inch of plywood is right here. The metal studs, they're these guys right here, the ones with the X's. And then batt insulation is this the squiggly type shape. And then you have the gypsum board. So you might have noticed that we have 7 different materials, but we have 10 rows. So something that you're always going to include in every single wall section you're going to have is an outside air film and an inside air film. Okay. So the reason why that isn't included is just that's a given. These are the building materials, and the air films just appear like naturally as a part of nature. So we can just start going down, labeling this. This is the face brick, 4 inches. Now, what is this? This is an air gap right here. So normally in a brick wall construction, I think you would have an air gap somewhere inside. I'm not really sure exactly how it works, but I'm pretty sure all brick walls have like an air gap somewhere. Don't quote me on that, but this one does have an air gap. So we'll just go down and just put in everything else. 1.5, wait. Vapor barrier. 1.5 inch. Polystyrene. Insulation board. Well, that fit. 1/2 inch plywood. 2x4 metal studs. Batt insulation. and then 5/8 of an inch gypsum board. So it's a typical wall. There's nothing really that special about it. It's just a normal brick exterior with a gypsum board interior. Nothing really special. So another thing, if you have trouble identifying materials in the wall, normally it's laid out in order. So this is going to go from outside to inside, but you'll have this like extra air gap. Normally, like the thicknesses will also be displayed correctly. So we have a vapor barrier that's relatively thin. We have the 1/2 inch plywood right here. So you see how that's thinner than the 1.5 inch insulation board. So if you're just having trouble, try looking at the thicknesses of each material as well. They might help you. All right, cool. Does everyone follow all this bit?
Yeah, I'm just printing out the paper right now.
Okay. Does anyone not follow?
Yeah, this is similar to what Van Landingham did with us, so
Very similar.
I recognize this. Yeah.
All right, we're gonna move on. So now we need R values. Outside air film. So we're gonna go down to here. This still air and moving air. This relates to outside and inside air films. So one of these is going to be outside, one of these is going to be inside. Moving air is going to be outside. Why? Because there's natural wind. Now, obviously, on the inside of a building, there's going to be like air movement as well, air conditioning and whatnot, but it's less dramatic than what's going on the outside. So moving air, that's going to be on the outside. You can see here we have a winter wind and a summer wind. The word wind also is an indication that it's going to be on the outside. It's going to be a natural breeze wind. So you have two R values here, 0.17 and 0.25. SI units, we're not going to care about that. So we're just going to look at this half of the graph right here. Because we're working in IP units, is essentially the imperial measurements. SI uses metric measurements. So you have like the kilogram, the meter, but in IP you have like the foot, the mile, the pound. So if you realize in architecture we're using like 6'8", 2 inches by 4 inches. We're using imperial measurements. So that's why we're using IP. If we were not in the United States, we would be using SI. We'd be measuring in millimeters, like 960 millimeters or 1,350 millimeters. But we're in the US, so we're using IP. So 0.17 or 0.25. Van Landingham says to always be conservative. And the reasoning is whenever you're estimating a insulation, you always want to expect it to be like less insulating than is. So you build up more insulation. The thing that you don't want is too little insulation rather than too much insulation. So if you have too little insulation, it's going to be super cold. If you have too much insulation, it might be a little hot, but you can remedy that. So what we're trying to reach for is overestimating. We're trying to accommodate smaller insulation values, smaller R values. So we're just going to use 0.17. I don't know if that made sense, but always use the smaller number, just so you have enough. All right, that was a big tangent. So now we're just gonna go down the list. 4-inch face brick. That's a masonry thing. So we're gonna be looking right hither. And since Van Lanningham was so nice, he only gave us one masonry thing. We have fired clay bricks. So we're going to look right here, and we're going to look under one of these two columns right here, IP resistance, R value. See the R in the parentheses? We're finding the R value. So there are two columns here, per inch thickness and for thickness listed. This is under per inch thickness because for the for thickness listed, these would have actual measurements. So you see here, this has a measurement of 0.25 inches and it's under for thickness listed. But here, there's no thickness listed, so it gives you a general value for whatever thickness your material is. So we have the R value is going to be between 0.12 and 0.10 per inch. So we're going to be conservative. We're going to use the lower one. 0.1 per inch. How many inches do we have? We have 4 inches, so that would be 0.4. Does that make sense?
Oh, so we're taking the low number and multiplying it by the number of inches, so it'd be 0.1 times 4.
Yes.
Okay, nice. Yeah, that makes sense.
Right. 0.40. All right. Air gap. This is another thing. How do I put this? So this isn't going to be listed anywhere on the table, and Van Lanningham says just to use 1 for the R value for all air gaps. So yeah, anytime you have an air gap, it doesn't matter what thickness it is, generally. But if you have an air gap in a Tech 2 problem, just use 1.0 for the R value. Vapor barrier. So we have a vapor barrier. So that's going to be right here, building membrane. Just like super thin. You see how thin it is compared to all the other materials? Super thin. It's like it's a film right here. We have vapor barrier. So we're just going to look across there and, oh, negligible. That's what NEGL stands for. What does negligible mean? It means it doesn't matter. What doesn't matter? 0 doesn't matter. So our value of vapor barrier is 0. And we're just going to move right along. The rest of these should be super simple. 1.5 inches polystyrene insulation board. Going to be under insulation, insulating materials, Wablamio. We have polystyrene right here. It says polystyrene right there. I don't know if, can someone speak up? Can you see that? Like, is it too small or too blurry? Do I need to zoom in?
I can't read it at all.
Ah,
Yeah,
shucks.
it's kind of hard to see. Since I printed out the paper, I can see it, but yeah, on there.
Okay. All right. Can y'all see it now?
Yeah.
Okay.
Run.
All right. I'll keep that in mind. So insulating materials, you have expanded polystyrene right here, and it's gonna have a per inch thickness right here, 5.0, 5 per inch. So you see here, it doesn't have like a listed measurement, so we're just gonna use 5 per inch. So how many inches is this? 1/2. 1.5 times 5, which is the R value, you get 7.5. 7.5. Moving right along, we have 1/2 inch of plywood. Looky here, building board. Building board, gypsum or plaster board. We're not having plaster, we have plywood right here. Looks like it's all going to be Douglas fir. So, and we do have a thickness listed, so we're just going to use that because we already have the thickness. We have 0.5 inches, which is half an inch. And we move over to for thickness listed, that's 0.62. So we're going to use that as our value. I'm actually going to see if I can just enlarge this. Resize 200. Oh, that's much better. There you go. All right. 100%. All right. 2x4 metal studs. Now this one tripped up a lot of people in the group chat. And this kind of tripped me up too because it's not anywhere on here. But I say this is one way to think about it. So R value, let's look over here. Insulation is, where is it? Insulation. So the R values of, the R values of insulation is high. So it would mean it would block a lot of heat going through. Now the insulation would be low for like thinner materials like plywood or something. See how low that is compared to insulation? So this would lead you to believe that the higher the R value, the less heat that goes through. Now, think of an electric stove. What sort of material are you using to heat up the stove? You're using metal. Heat easily goes through metal. So we're just going to use 0. Or at least I'm going to use 0.
I looked it up, and it says that metals does not like account. They're always put at 0 because it heat up fast.
Yeah. So you said 0?
Yes.
Or, okay. Yeah.
So
I also
like the vapor prayer, it's the same thing. Like, well, 5. I think Professor he used like 5 the circle, but you could put it 0.
Okay. I also have this textbook that I also looked at, just to double check materials. So it's called Building Construction Illustrated, and it says here for metals it's like 0.001 for the R value. So essentially 0. So we're just going to use 0.
So it's the same negligible, right?
Yeah.
Okay.
Probably. It's not on the chart, but the way I see it, I think it's 0. I could be wrong. Other people could be wrong. There could be a weird correct answer. But
I think
this is all we have to work with.
If I get it wrong,
Yeah,
I get it wrong.
If you get it wrong, you get it wrong. And I'll hopefully host a follow-up to correct stuff that I said. Because a lot of stuff I say might not necessarily be correct.
I mean, I just took a quick glance at our notes that we took, and I remember when he did it, he put 0 too.
You did? Oh.
The
well,
2
I
by
didn't pay attention in class then.
I'm dead. No, yeah, because in class he labeled it 2x4 pine stud, and I've got it listed as 0 for the R value.
Well, that's for pine.
Yeah, facts. Yeah, I don't know. I don't know what he's playing games, bro. Fuck that guy.
No, he did not put it 0 in the lecture because it was a wooden stud.
Wait, really? Then what is 0?
I think you mean by the bat insulation.
He put that as 0? Oh, my bad. I got confused because you know what? He had 2 columns. He had R at the stud and then R in between. So
yeah, we'll get into that.
Yeah. We'll worry about it.
All right, so we're just going to move on bat insulation. So we're just going to look over here, bat insulation, Weblamio. Right here, insulating materials. We have blanket and bat, and we're going to use this bits right here. Now this has like a bunch of listed measurements right here. Approximately 3.5 inches, 5.5 to 6.5, 5.5, 6 to 7.5. What's the thickness of this bat insulation? So because it's in the same like sort of area as the 2x4, it's gonna be the same dimension, same thickness as the 2x4. So if you remember, sorry, what was that?
So we would say that since the most studs are angled horizontally, so the vat insulation would be about 4 inches thick then?
Yep, about 4 inches thick. Now I say about because if y'all remember back in Tech 1, you have, what is it, nominal dimensions and then actual dimensions. So I'm just gonna bring up that page real quick, if you guys do not mind.
I would say it's about when it's wood, but here it's metal.
Well, yeah, but where is it? So it says here on the thing, it says, hint, what's the depth of a 2x4? So he's hinting that's going to be a special case. But like, I don't know about metal studs if they're 2 length, 2x4, but I'm just gonna, for purpose of this, you don't have to follow along with what I say, but for the purpose of this, I'm gonna assume that's not 2 inches by 4 inches.
I'm gonna agree with you right there, Edison, because making my head rack, not all the metal pieces that say that they're 2 inches by 2 inches or 1/8 inch thick by 2 inches, they're actually sometimes they're thinner than that. Sometimes they're like 1.75, 1.5. So yeah, it's actually correct to think that about metal studs too.
Right.
But the
So
steel
this
is also the steel.
Yeah, so this is just a screenshot from the textbook. You see nominal dimensions, you have 1 inch, 2 inch, 3 inch, 4 inch. And you see here actual dimensions, you have 3/4 of an inch, 1 and 1/2 of it, or 1.5 inches, 2.5 inches, 3.5 inches. So we're just gonna, I'm just gonna use this as reference. So you see 4 inches is the nominal dimensions, and then you have the actual dimensions, which is 3.5 inches. So we're gonna assume that this bat insulation is 3.5 inches. And this also works out too. Oh, that would make sense anyway. So we're just gonna assume it's 3.5 inches, and that works out for us too, because if you look here, see right here, approximately 3.5 inches. So it matches up exactly with what measurement we have. If you would have 4 inches, then you'd be like, there's not really a thing for that, so you would just round to like 3.5 inches. So you would end up with this either way. So our value of a 3.5 inch of insulation is 15. So we're just going to write that 15. Right. Then gypsum board, we are going to 5/8 of an inch. Just going to look here, gypsum 5/8 of an inch. What's 5 divided by 8? 0.625. We can use this row right here. And we're going to use the 4 thickness listed. Entry data point right here, 0.56. Inside air film. Now this is back to the still air, moving air. This one's going to be the still air instead, because there's not a lot of wind inside. It's much less intense than the outside environment. So we have a bunch of different stuff right here. So we're just going to go through them. Position of the surface. How is the wall positioned? Obviously, it's vertical. And then the direction of heat flow is going to be directly perpendicular to that, horizontal, because it's moving in and out right there. So we're going to be, we have a bunch of different R values. We have this R value right here. We have this R value right here. And we have this R value right here. Which one do we choose? We're going to be conservative. So we're going to choose the lowest of them. That would be this one, 0.68. So our R value for the inside wall is 0.68. Beautiful. Does anyone not understand?
Hello.
Hello? We good to move on? Beautiful. We're just going to move on to the second page. We don't need this anymore. And I'm just going to get a screenshot of the second page. Wablamio. Second page. Yeah. All right. Cool. So we got this boy. So now we have to calculate the U value. What's the U value? It's just the inverse of the R value. If you look at the slides that he gave, I believe the formula was U is equal to 1 over the summation of R. I believe that was the formula he gave. So this is exactly what we're going to do. We're going to take all the R values, add them all together, and then we're going to inverse it. We're going to put it upside down, going to divide 1 with it, and we're just going to get the U value. So this is slightly tedious. We're just going to, you know what? I'm going to be smart. Control C, Control V. There we go. Beautiful. Okay. So we have all the components. We have them right here. And then we have we're calculating different R values for at the stud and between the stud. Now, what does this mean? So if you look here, we can, I think I should just get a better screen or whatever, we'll be fine. So if you look here, if we draw a line through the wall like this, it's going to hit every single component except for the metal studs, right between the studs. It's going to hit every single component except for the studs right there. Right? So that would be R between the stud. As for at the stud, I'm going to draw a line right here. There's just going to be another section right there. We're cutting directly through the stud, but not through the insulation. Does that make sense?
Yeah.
Does it
Yeah.
not make sense? Okay, cool. So we have R at the stud, cutting through the stud, not the insulation. And we have R between the stud, cutting through the insulation and not between the stud. So we're just going to copy all these R values over. We're just going to skip out on those stud values real quick. So for at the stud, we're cutting through all this outside air, brick, air gap, vapor barrier, insulation board. Remember, this is different from the bat insulation. The insulation board's right here. The fibrous bat insulation is over here. Well, I just realized I just decimated that. We have that. And we're going to put that in between the studs as well. We're looking at these materials right here. So regardless of where you cut through, you're always going to cut through these 6 materials. These 6 dots, 1, 2, 3, 4, 5, 6. Right. So then at the end, we're also going to have the bat insulation. Oh gosh. Also going to have the bat insulation. That's not fun. Also going to have the bat. Wait, not the bat insulation. What am I doing? We're going to have the gypsum board as well as the inside air film. Right there. So no matter where you're cutting through, you're always going to cut through these boys. Right. So R at the stud. Okay, I'm going to start with R between the stud real quick. I'm going to start with the bat insulation, just so this concept is clear. So bat insulation, we're going to look for between the studs. Is bat between the studs? Yes, it is between the studs. So we're going to include this R value, which is 15. Oh my god, this doesn't want to. 15. It's between the studs. Now, is there insulation at the stud? No, because the stud's there. So it's going to be 0 because it's not there. So there's no R value because it's not there. Cool. And we're going to do metal studs. All right, metal studs at the stud. Is the stud at the stud? Yes, we're going to use this R value right here because it's at the stud. Oh, look, it's 0. Now, between the studs, is there a stud between the studs? No, it's insulation. So it's going to be 0 because it's not there. It just so happens to be the same because the R value that we wrote was 0. So both of them ended up to be 0. If this would rather be 0.1, then this one would be 0.1, and this one would stay 0 because we're going directly through the stud, and the stud is at the stud. Does that make sense? I hope it does.
Yeah.
So
Beautiful.
it says to show work. Exactly how would you do that?
So I don't know. This is
Fair
what
enough.
I'm gonna do. You can take your own liberty on how you want to approach it. I'll like discuss a few different ways that you can. So one thing you can do is
I would assume since we had to print it out, he would want to see markings on the chart.
I should do that. That is a good point. Yeah.
So I'm
Yeah,
gonna
mark your chart. That's a
I'm
good
gonna mark
point.
the chart.
Bro, yeah. So what I did was I circled all the R values on the chart. I just circled them and you know, like I drew on it with a pencil.
And then I accidentally made some mistakes on this paper, so that shows a little bit of work. Like, oops, I did something wrong.
Well, I'm also doing it in Illustrator because I didn't print it.
Right. So
Yeah.
even in Illustrator, I would take the circle shape and then on your chart, circle all the correct R values and like underline them in the chart, and then send the chart in as part of the PDF that you turn in.
Mhm.
Alright.
Damn, why didn't I think of that? You guys are smarter than me.
Whoa! That's a big statement.
Says the person
Oh, hold up, man.
Yeah.
Watch out there.
Review
I don't know
session.
about that. Not gonna lie, Edison. I messed up my head rack not once, not twice, but 3 times already. So you're smarter than me. I can tell you that right now.
Okay, yeah, thank you. All right, so we're just gonna, so this is the way I did it. I'm just gonna add up all the R values, so we're gonna get a total R value at the studs. So can someone just add up all these values for me?
Yes.
Beautiful. Where's my calculator? There it is.
All right. So for R at the stud, I'm getting 9.69.
9.69. All
I
right.
don't know if anybody else wants to double check me on that, but that's what I got.
Yeah, what did everyone else get? So Imran, you got 9.69.
Yeah.
Did someone else get a different answer?
To be honest, I didn't do it because I'm marking my sheet. So, sorry.
All right. And then for R between the stud, I got 25.93.
5.93.
I got the same thing as Imran.
At the studs
Between the
And-
studs.
or between the studs? Okay.
What
What
about
about at the studs? Because
What did y'all say it was?
9.69?
so I actually didn't get this number.
No.
I think you didn't add something.
Yeah,
I
because
got
I'm
it.
adding it, I'm getting a bigger number each
Wait.
time.
Is it 10.93?
It's 10.93.
Yes,
Oh,
I
okay,
got
my
that
bad.
one.
My bad.
Okay, I was scared for a second. I was like, I don't know what I did wrong, but I got 10.93.
My
So
bad.
that's why I was
10.
asking for other people to do it.
I had
Yeah,
to
that's-
double check. What did I
Yeah,
notice?
just double check. I will bring up something real quick. So there's another thing you can do to check. You see here, all these values are the same, right? Blam, 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 blamio.
Mm.
These values are all the same. It's just these values that are different between the at stud and the between stud. So if the difference between these two is not the difference between these two, then you're doing something wrong. So see here, both of these columns add up to 0, but both of these columns add up to 15. You see this number plus 15 does not equal this number. So just another way you can check is,
Oh, you just
just
minus it, right?
yeah.
Oh.
So just 25.93 minus 15, because this is the difference between the two data points that you, or two sections that you got. So you can literally just take 25.93 minus 15, because this is extra, and you get 10.93. Oh gosh, 10.93. See how that correlates? You have this group of numbers right here, which they're the same. You have this group of numbers, which are also the same, but this group of numbers is different. So the difference between the value would be reflected in this box. Yay, nay?
Yeah, I agree. And I just made a mistake. I put like a minus sign instead of a plus sign. But I like this way of checking your answer because you know that the bat insulation metal sort of special. Like,
Yeah, I
can
think
check
you
it.
put minus on the plywood, but it's
Yes, how'd you got that correct? Yeah, you got that actually correct. Yeah.
fine. All right. So beautiful. Now we have the R at stud, the R value at the stud, R value between the stud. So now we are going to do something with that. Fergus. So this is what I did. Now we're just gonna find the percentage of the wall composition. So imagine this wall right here. There's a lot of markings on that, but we'll be fine. So if you look at this wall right here, I'm actually just gonna, oh my gosh. You do not want to. Okay, there we go. We're just gonna look at here. So you have the stud, right? This. Oh, okay. So you have the stud here. You have the stud here, And then you have the insulation in between the studs. So obviously it's not the same composition throughout the entire wall. There's some places where there are studs, there's some places where there aren't studs. So what do we do with that? We just take like the average. Well, not the average. We're not going to add both of them and divide by 2. We're going to take the weighted average. So essentially we're going to take how much this percentage is right here, and we're going to take this percentage right here. So you see how this is much bigger than the studs? It's going to be important. So back to the studs real quick. We know the 2-inch, the 4-inch is 3.5 inches actually. I'm gonna have the 2-inch measurement is gonna be 3.5 inches. Or frick, the 2-inch measurement is gonna be 1.5 inches. Remember, that's from the optimal, or whatever the frick it was called, the nominal and the actual dimensions. So just something to remember from Tech 1. Right, so 1.5 inches, that's this thickness right here. This is 1.5 inches right there. I'm gonna draw this in blue. This is 1.5 inch thickness right here, and that's the 3.5 inch thickness. So when taking a weighted value, which dimension do we care about? Well, let's think about this. If we have a line right here, this is our air that's going through the wall. When it passes through the wall, which dimension is it hitting? Is it hitting the 3.5 dimension or the 1.5 dimension? Which wall is it?
Gonna smack that 1.5 across the face.
Yeah. So you see here, right here, it's hitting that 1.5 inch, 1.5 inch. It's not hitting the 3.5 inches. It just travels through 3.5 inches. So we're gonna use 1.5 inches for as part of the weighted average. So so we have the thickness of the studs, but now we need to know the thickness of the insulation. How would we go about doing that? Well, we can see here we have the 2x4 metal studs, and they're spaced at 24 inches on center. Now, what does that mean? You have 2 studs, and at their center points, right there, I'm going to draw this in red. At their center points right there, center point, there, the distance between these 2 center points is going to be 24 inches. 24 inches. Now, why is that useful? Well, now we can use these 2 measurements, this 24 inches and this 1.5 inches, to figure out the thickness of the insulation. Now, you don't really need to do this. I'll show you why later, but we're just gonna do this just to have a thorough understanding of what we're doing. So I'm just gonna redraw this real quick. So we have this imagine this as the 24 inches. You have, geez, crikey. You have the stud right here. That's not what I want. We have the stud right here. You have a stud right here, right? So at the center points, it's going to be 24 inches. So you see, we have 1/2 of the stud right here. So that's 1.5 divided by 2. We have another half of the stud right here. 1.5 divided by 2. Add both of those together, you just get 1.5. So the percentage composition, or just the composition of a stud in one of these sections is 1.5 inches. Got half of it from here, from this boy right here. We got half of it from here. So it's just a whole stud. You can also think about it like this. So right now we're doing it on center, but what if we don't do it on center? What if we do it on left? Or just, this isn't a tech term, but left, you know? So we just took these two right here, and we just scooched them over to this side. So you see now we have this 1.5, oh gosh, pencil. 1.5 thickness right here, 1.5 inch thickness, and 0 inches right here, because we're not cutting into the other stud. So we have our 1.5 inches again. What you don't want to do is have different reference points. So you see here, the start of this dimension is on the left side of the stud, but the start of this dimension is on the right side of the stud. Now you'll get an incorrect measurement because you'll have 1.5 plus 1.5, which would be 3, which is not the measurement we were looking for. Different ways to think about it. I am over-explaining. Hopefully that didn't confuse you. If that did, just disregard what I said. We're just gonna focus on this right here. So I know this is a long tangent, but I just want to make sure you guys get the concept. So we have 1.5 inches. This is going to be 24 inches. And 1.5 inches of that is going to be studs. So what is not the studs is going to be the insulation. So 22.5 inches is going to be the insulation. It's going to be the bat. Sorry, that was like a super roundabout way of getting to these simple numbers, but hopefully someone found it useful. If not, then I'm sorry about that. Anyway, so we can take the 1.5 inches, and we're just going to take the percentage of how much that makes up this like small section, this 24-inch section. So it's literally just going to be 1.5 inches divided by 24 inches. And you're just going to get, can someone do that for me real quick? 1.5 divided by 24.
Uh, 0.0625, yeah.
And confirm that's exactly what I got.
0.0625. What does this mean? It's just basic math. 6.25% of the wall is comprised of stud. So we just move the decimal places two places over, and it's just 6.25% of that is stud. And now the other one is, you don't have to do like 22.5 divided by 24. You can just do like, think about this. You're just going to be dividing by 24 inches, right? And you're just literally taking what is not the stud. So you can just go 24 inches divided by 1.5. I don't know if you can see that well enough.
Wait, is it 24 minus 1.5?
Yeah, 24 minus 1.5. That's how we got 22.5. Did I say something different? Did I say 22 minus 1.5?
No, you're good, you're good.
Okay. So 24 minus 1.5, that's going to be 22.5. Divided by 24, what did you get?
0.9375.
0.9375.
Santos, what did you get? Or anybody?
What, the 22.5 divided by 24, right? So that's 0.9375.
All right, bet.
So you have 6.25% of the wall is made out of studs, and then 93.75% of the wall is made out of insulation. And you can just do a quick double check. Add these two values together, you get 1 or 100%. So that's just one way you can double check your work. Now, let's start calculating the let's calculate the average value of average R value across this entire 24-inch section. So we know this much percentage of the wall is comprised of a stud, and this much percentage of the wall is comprised of the insulation between the stud. So how do we work with that? You just have 10.93. That's my mother's cooking jalapenos. So you have 10.93, and so that's the R value at the stud. Now, what percentage of the stud makes up the wall? 0.0625 plus. Now we have 25.93. 0.93. Now that's the value, the R value that's between the studs. Now, how much is there? How much of the wall is between the studs? 0.9375. And you can just add those two together and you can get an average R value. So someone just put that into the calculator real quick. Tell me what you get.
Okay, I got 24.9925.
All right. Cool. Did anyone else get anything different? No, no one got anything else different? Yeah, me neither. So yeah, it's 24.9925. And then remember, we're trying to find the U value right here. U value. What do we have right now? We have the R value. What is the U value? That's the inverse of the R value. So you can just raise that to the minus first power or divide 1 by this number. And then you'll get that's
Wait, why did you do the up value like Y01 there?
so remember this is weird. So we have 1 divided by, so remember U is equal to the summation of the R values. So we're just literally dividing this by 1. Or dividing 1 by this number. Oh gosh. We're just going to take this number and we're just going to put it under 1. My gosh. And we're just going to get the U value. Now something is weird.
So,
Okay.
what's up? You want me to tell you what I got for 1 over that?
Yeah. What did you get?
0.04.
Okay. That's what I got, but something's weird on my end. On my paper, I did it a different way. Give me like a minute real quick. Let me
Wait,
just double
Ron,
check.
what'd you get? You got 0.040012, right?
Yeah. It's a
Oh.
much longer number, but I just didn't want to add the rest of the numbers.
Oh, okay, yeah, I was just making sure. Like, wait a minute.
No, you're right. I got that too.
Okay. Just small error on my thing. That should be the correct number, but
The 0.04 number?
yeah.
Okay.
I think I did something wrong on my worksheet. Let's see. 1 divided by.
Number of people here is slowly getting higher.
Slowly getting higher? I thought it would get lower. Oh my god.
No, there's 19 people now.
It's been going up. It was like 14, now it's 19.
I thought people were leaving because I was
Yeah.
being too boring.
Yeah, when I got here, it said +6 at the end. Now it says +10.
Yeah.
You're not bored.
Aw. But this is weird. Hold on. Oh my gosh, this is not going. Y'all give me a minute, real quick. This is being.
Emron, start a timer. 1 minute.
So I turn 1 minute? No. Edison can have all my minutes. He can have all my minutes. All the rollover minutes are his, bro.
It's so weird having so many people in class this time.
Right? In class. See how you call it class? This is class to me, man. This is the class I'd never miss right here. This
For
class.
real though.
And I was talking with my studio mates the other day. They were like, "Yeah, man, screw tech. I'd rather sit in studio for an hour longer." And I was like, "Yeah, man, of course, I agree."
Honestly.
Not wrong.
Man.
Alright.
My legs have never been this sore before, Emron.
Oh God, you've been
Because
working hard today.
all the squatting and kneeling just to weld my head rack was just, man, I'm
Right.
all for all my legs.
I gotta ask, did you use a TIG welder or a MIG welder? What kind of welder are you using?
I went the lazy route. I went the MIG welder.
Oh, okay, because I used to weld in middle school and I miss it. I haven't welded since then, and it was the most fun thing ever, welding.
Sounds like bacon cooking.
Yeah, it is. Welding is something special, man. I really want to get back into it. How much does it cost, a MIG welder? Do you know off the top of your head?
Ooh, you get them fairly cheap, but I'd say for a good MIG welder like a Lincoln Electric like I was using, I'd say about maybe $2,000.
Wow, I think I'll just buy a laser cutter instead.
I was about to say cheap. Really?
At the same price.
Cheap for them, maybe.
Oh, like a cheap one? Oh, a cheap one? You can get one on Harbor Freight, maybe 5,000. I mean, not maybe 500.
Okay, I'll have to think about that because welding is just fun. And it's an art. I think welding is an art because you can have nice welds, you can have bad welds. So,
Yeah.
Because when I first welded, it was terrible, Santos. My welds were so ugly. But then slowly over time, I became a nice welder. But that was in middle school, and I haven't welded since then. So
Nah, see, most of my welds on my head rack right now, they're nice. But the wind picked up and it moved the gas that comes out of the gun out of the way.
Mhm.
So it was popping on me. So I had like all these like ugly looking welds like halfway done with it. And I was just like, oh no.
Okay.
Looking at it right now, you could get a MIG welder for $500. Harbor Freight.
That's actually not bad. That's I'll just sell my Xbox. The Xbox makes me no money. The MIG welder will make me money. So
Heck yeah, man.
um,
But you want a link? But if I were you, I'd get a Lincoln Electric or a Miller. Those are always good brands.
okay. I'll take your advice. You're the expert here.
I wish.
And
All
I
right.
hear you. Yo, what's up, Edison? You ready? Let's go. Let's get it.
Yeah. Sorry to cut you off. Just you
No,
can
you're
finish
good.
your thought.
No.
Oh,
I
you
have no thoughts. You are my thoughts. I only think about
Whoa! Don't be calling Edison a thought now. You hear?
Oh my god. You crazy. Alright. Alright. Disregard this. Jeez. Okay. I'm sorry. Okay. So, I just looked back at the lecture and I realized I did it. So I got two different answers. So for the homework, I did it one way, and for this presentation, I thought it would be easier if I did it another way, but this is actually the wrong way, apparently. So we're just gonna yeet that out of the way. So this is what we did right here. So you have the U, we're trying to find the U value. So what we did is we took the inverse of the R value of the R value, 1, times the proportion, 1, the percentage right here, plus the R value of the second one times the proportion of the second one. And we just divide all that by 1, or divide 1 by that. So what you're actually supposed to do is you're supposed to take 1 divided by the R value, 1, times the proportion of 1, plus 1 divided by the R value of the second one times the proportion of the second one. So how is that different? I don't know. You get different answers. I think I'll figure that out hopefully sometime in the next hour. So what we're actually supposed to do is we're supposed to convert from R values to U values and then multiply it by the percentage. So I'm just gonna, so this little bit right here, we're just gonna eat that out of the way. So we're just gonna try this again. Sorry, I just want to make sure we got the correct answer. So we're just gonna do what I did. We're just gonna take 1 divided by 10.93, right? So we're gonna get the U value right here. And then we're gonna multiply it by, okay. So you see, oh gosh, that's not right. So you see here, we're calculating the U value right here because remember, the U value is the inverse of the R value. So we're first going to calculate the U value, then we're going to multiply it by the percentage. So you see the difference here is the first thing that we did is we took the R value multiplied by the percentage. We're supposed to take the U value and multiply it by the percentage. So first convert to U and then add the percentages. So we're just going to do that instead. Does this make sense? Does everyone understand why this is different?
Yes, I looked back at my notes and I see this is how Van Landingham had done it.
Yeah, I thought it would be easier the other way, but you get a different answer, so it's not the way you're supposed to go at it.
I can see this way is the correct way.
Yeah. So if you see here, like these two formulas, they're not the same.
Wow, wait a second. So you get a different answer, but so slightly, right?
Yeah.
It's like slightly different. So the first time we did it, I got 0.040012 something. And then this time I get 0.04187.
Yeah. Is everyone else like seeing the same thing?
It's
like
close, but it's different.
Yeah.
It's still different, yeah.
So this was the value I was trying to get to. Not the 0.04001, but this value instead. Hopefully that didn't trip up anyone, right? So if you just look here, this is not the same as P1 over R1 plus P2 over R2. So this is what you're supposed to do right here. This is not what you're supposed to do. This is not what you're supposed to do. You're not supposed to calculate the average R value and then find the U value. That the U value that would correspond to the average R value. You're supposed to find the U values of each individual R value and then put it all together. So like the way he wrote it is he put U average is equal to U at the stud plus U between the stud. So see, we're taking two separate U values and putting them together. We're not taking an overall R value and just flipping it. You're calculating the U values for every single component, and then you're adding all the U values together. So that is what we get. Did that confuse anyone? I hope it didn't. If it did, can someone say please? Someone please say something.
I'm a little bit lost.
A little bit lost? All right, which bit are you lost on?
Just towards the part where you change the equation to like make it more similar to Josh's.
Yeah. So, like, you're confused about the question, the equation itself.
Yes.
Okay. So, let's see. I'm just gonna take this out of the way. So this is the correct way. I'm gonna write this in blue. U average, taking the average U value, and we're gonna take the U value at the stud and the U value between the stud, right? Times their respective proportions, of course. And like, if you think about it, yeah, that's how you take an average. See, how do I do this? So like, let's say you have an average, you like, yeah, think about to the cooling and heating degree days. You have an 85 degrees, you have 105 degrees. When you take the average, you take this plus that divided by 2. So you're essentially bringing two different values together, right? You're bringing the two different values together, and that would be 95. Now what I did, I'm going to write this in red because it's wrong. Took the average U value is equal to 1 over the average R value at plus the R value between. So there's like a slight difference between these two equations. It's only slight. It's like some crazy thing that I haven't figured out yet between the numerator and denominator and how fractions work. So you see here, we're calculating the average R value right here. So I'm just going to rewrite this as R average. And we're just going to do 1 over the R average, and we're going to get U average. That is technically correct. Like, if you divide 1 over the R value, then you would get the U value. But this is not what we're supposed to do for weighted averages. Does that kind of make sense?
Yes.
It does?
Thank you.
Oh, wow. I did not expect that to make
Yeah.
sense.
No, I get what you. I was just confused because like usually you like to get an average you divide it by the amount of the quantities you're averaging, but since it's different values.
Edison, don't forget, technically correct is the best kind of correct.
All right. So I think I have a small picture in my mind that I kind of want to illustrate real quick. So we have, hopefully this will make sense. If it doesn't make sense, just disregard this. So we have, this is a graph of what we're doing. So right here, this is like a graph of our process. So right here is where we're gonna be calculating these two. It's like, imagine this is the R value at the stud. And this is the R value between the stud. So we're taking all the average R values, and we have the average R value, right? Average R values right here. And then we're going to convert them into U values right here. So now we're going to convert them into U average values right here. So you see how there's still two separate values, but now they're converted into U values, and then we add them together. This is the correct way to do it. And then right here, you arrive at a point where you get the U average value. But what I did is I first brought them together, and then so I got the U value. So, or I got the R average value right here. Gosh. Got the average R value right here. And then we converted into U value. Oh, I underlined. There were ways to do it, but the way that we did it was the wrong way. And the other way was this way. Where is the... No outline. To see, we did this. Oh god, outline. Solid color. So first we converted them into U values. And then we combined them. So you see right here, we combined them when they were R values. That's not the correct way to do it. But here we combined them when they were U values, and this is the correct way to do it. Now, this image just sort of appeared in my mind. But you see, like, we did different operations at different times, but that led to completely different answers. So do all the conversion first and then add them together. Don't add them together and then convert, I guess is what I'm trying to say. Does this kind of make sense? If it doesn't, it's fine. Or did this further confuse someone?
I think the important part was the wording. Do all conversions first, then add. I think
Yeah.
One thing
That's
to remember.
Get at.
Yeah. I mean, Jason, does that make sense to you? Do all the conversions first, then add?
Yeah, perfect.
Oh god, that's not what I wanted. No fill. So this is yes. This is no. All right. So now that I've gotten off of that tangent, oh my gosh, that was a long tangent. We're gonna move on to the last bit of the homework, which is calculating temperature, average temperature. Let's see.
Wait, so what's the final answer for this one? Is that what you have?
All right, yeah, 0.04187, or however many decimal places you want to use. Cool. So we're just gonna, let's see. How am I going to screenshot? Screen. All right. So now we have this last bit problem right here. So gonna do a lot of math. It's gonna be very repetitive. So brace yourselves. Question. I don't know. It's gonna be a lot of repetitive stuff. So I think I'm just gonna just fill this out. So essentially what we're doing here is we're basically using the R values, the different R values that each material has, and predicting what the temperature is going to be throughout the entire wall at different points of the wall. So they're like a few points of interest. There's this point of interest. I'm just going to draw lines because it's going to be the same. This point of interest right there. This is before the vapor barrier, and this is going to be after the vapor barrier. After the insulation, after the plywood. after the bat insulation and studs, after the gyp, after the air film, and then I guess, well. So there are a bunch of different points of interest right here. And if you remember, each of these, if you can observe, each of these is a different, correlates to a different wall material, right? Air film, brick, air gap, vapor, insulation, or polystyrene insulation, plywood, insulation, and studs, gypsum, inside air film. So see, each of these is a different temperature, or is a different wall material. Now you see here, 97 degrees Fahrenheit. This is the outside temperature. Outside temperature. 74 degrees. The air temperature is lower. So essentially what we're going to draw is like a small graph of what the temperature would be. So just think of this as a graph. So this would be 97, midpoint right here. I'm just going to draw this in gray. Midpoint right here, that would be freaking, I don't know. That would be like 86 degrees. Make this bigger. This would be like 86 degrees. Why is that underlined? 6 degrees, right? And then like up here would be, what's that, like 92 degrees Fahrenheit. And then down here, this would be like 80 degrees Fahrenheit. So it's like a graph. Essentially what we're going to do is, as we move through this wall, the temperature is going to change. So it's not going to change much through the air film. It's not going to change that much through, I'm going to use a thinner line. It's not going to change that much through the air film. It's not going to change that much through the brick. It's going to change quite a bit in the air gap. It's not going to change that much vapor barrier. It's going to change a little bit more in the insulation. Not that much in the whatchamacallits, the plywood, and it's going to change a lot in the insulation. Change not that much in the gypsum, and you're supposed to get down to here. So essentially, we're trying to find this. Trying to define the different points inside the wall, what the temperature would be. So that's essentially what we're doing here. That makes sense? I'm sorry, I forgot to ask. Did that make sense?
Yes, it's similar to what he drew in class too. Reminds me of that.
Yeah. So this is just like essentially just a different another explanation of how what he's doing.
Roger, Roger.
Beautiful. Okay. How do we do that? So luckily we have math on our side. Math is great because it is always the same. So let's see if I can, come on. No scroll bar, no scroll bar, okay. So math is pretty cool because it can provide approximations of what temperatures different temperatures is going to be in the wall. Now, let's see. What was I going to say? I was going to say something. Right. It's whatever. So, oh yeah, that's what I was going to say. So one cool thing, I'm just, while I'm talking, I'm just going to fill out all the components right here. So one cool thing about finding air temperature is that the change in air temperature is directly proportional to the R values. So if the R value changes like 1, then the temperature is going to change a certain amount of degrees. If the R value is 2, then the air temperature is going to change like 2 times the previous amount of degrees. So like the higher the R value is, the more the temperature is going to change. And yeah, so if you think about it, like R value, that's a measurement of insulation. The more insulation there is, the more the temperature is going to change because there's more insulating material. If there's less insulating material, then it's going to not change that much, the temperature. That's probably just spitballing, so maybe that didn't make sense. Hopefully it made sense, but it's not really that important if you didn't understand gypsum board. Inside air film. Cool. So we have all the different components right here, and we're just gonna take their R values. Excuse me. We're just gonna take their R values, and we're just gonna use this column. So really, we should have used the table from the first thing, the first assignment, the first activity that we did. Let's see. Should use this paper with all those values listed out, but they just transferred over to here, but they're the same. So we're just going to use this because it's right here. Cool. So air film R value, gosh. Air film R value, 0.17. Face brick, 0.40. Air gap, 1. Vapor barrier, 0. Insulation board, 7.5. Plywood, 0.62. Metal studs, 0. That insulation, 15. Gyp, 0.56. That's not 5. 0.56. And then inside air film, 0.68. Makes sense. Cool. All right. Moving on. Now, a question did come up, or a problem did come up while I was doing this. So it says on the assignment, it says at the top in italics, hint, use the weighted average to calculate. Use common sense to see if your answer makes sense. So we're supposed to do something with the average weighted values that we did. So something about the percentage of the wall composition with the studs and the insulation. Now So I don't know what anyone else did, but this is what I did. So I'm just gonna assume, so these two, these are the main culprits right here. The metal studs and the bad insulation, right? Because they take up the same plane right here. You see right here? This plane right here, they take up the same area. So I'm just gonna, and I hope this is correct. Wait, hold up. Divide by. Okay, so All right. I might have done it wrong, but there might be another way that's less confusing. I'm just gonna do what I did for the homework. You might be doing something different, and if you are, then cool, go for it. But this is the way I'm gonna do it. It might be right, it might be wrong. I just don't know. If someone else has a different way to do it, then please tell me, because I could very well be in the wrong here. But anyway, this is what I'm gonna do. I'm just gonna multiply it by the percentage that it takes up the wall. So the bad insulation takes up 93.75%, and the stud takes up 6.25%. Right? So I'm just gonna multiply it. Whenever I add them to the cumulative R values, I'm just gonna multiply it by these values. It might be wrong, but it's the attempt that matters. And I don't have the answer key, so I could be doing it wrong. Anyway, so we're just gonna add up all the R values. So I'm gonna ask you guys to do this. So what's 0 plus 0.17?
0.17.
Gosh, that's crazy. What's 0.17 plus 4? 0.4.
0.57.
57. 1 plus 0.57.
1.57.
0 plus 1.57.
1.57.
7.5 plus 1.57.
9.07.
7. 9.07 plus 0.62.
9.69.
9.69. 9.69 plus 6.25% of 0.
I say that's zero.
9.69. Now this is a little tricky. 9.69 plus 93.75% of 15.
$24.69.
So I'm actually gonna.
Wait, so it's 15 times 0.9375 to get
Yeah.
the right? And so,
And yeah.
okay. So 15 times 0.9375 is 14.0625.
Yeah.
And then that number plus 9.69, I got 23.7525.
Yeah. So that's what I got. This could be wrong. I honestly don't know where I'm going with this, but this is the only logical way I could see it. So we're just gonna use this. Right. So 23.75 plus 0.56.
Cool. 24.31.
Finally, 24.31 plus 0.68.
24.99.
4.99. Does that make sense for everyone?
Yeah. Wait, did we do this type of thing in class? I don't know if I remember this.
I don't know. I know he showed a chart. Maybe we did in class. I didn't participate.
Yeah, I don't even remember this, honestly.
I don't know. Out of all the pictures I have taken of this screen, I don't have anything that looks like that.
Yeah, that looks like this. Thermal gradient through the wall. Like, what?
Oh, wait a minute. No, I do have something like that. It looks like this.
Yeah, that's essentially what we're doing.
Yeah,
Oh.
that's just the picture I have.
That is what we're doing.
Oh, okay.
So this then comes the tedious part. Gosh. Okay. So remember what I said earlier? Okay, just real quick. Does this make sense to everyone? Does this not make sense to everyone? Comments, questions?
That makes sense. So it's just saying how like you start with the outside air, and as you get more inside, the R value increases, right?
Yeah.
Okay.
Yeah, that makes sense. The only part that doesn't make sense is the bad insulation, but all of us are just confused on that one.
Yeah, I'm confused on that. So
Are you basically just adding the cumulative with the component, like each column until it increases, right?
yeah. So what we're doing is we're taking this value. I'm gonna make that thicker. Taking this value, and then we're gonna add this value to that, right?
And
And we're
it
gonna
just
bring it down. Yeah, and we just keep going. This value add to that, bring it down. So we get this value add to that, and then it just goes all the way down. So we're literally adding up all these values right here. Adding up all these values, and that would equal this value.
Okay, thank you.
Right. So
Yeah.
yeah, as you progress through, you're just adding more and more and more. Any other comments, questions? All right. Let's move on.
I'm guessing this is where it wants us to show our work because it literally says show math.
Yeah. So we're gonna do exactly that. Gosh. All right. So remember what I said that the R value is directly proportionate to the change in temperature of inside the wall. So we're literally going to take the difference of this. We're going to take this R value right here. I think I'm just going to do it real quick. So we're going to take this R value, this cumulative R value. So this is a sign of like how far we are into the wall. So right after the outside air film, we're not that far into the wall, so it's going to be a relatively low number. Now, what is the percentage of that R value of the entire wall's R value? That's 0.17 divided by 24.99. Does that make sense? So we're
Will you
taking,
zoom in on that chart?
oh my gosh, really? You can't see that? All right.
I'm blind, okay? I'm sorry.
No, my internet's bad. That's the reason. So 0.17 divided by 0.2499. I'm going to do a little graph. So right here, remember all the vertical lines that we drew right here? I'm just going to draw those in again. Why aren't you? Okay, cool. All right. So essentially what we're doing is this 24.99. We're going to imagine that as this entire fingerino right here. This entire measurement right here, 24.99. So now this isn't a measurement of distance, so it's not going to be to scale. It's a measurement of the R value. So it would look more like this, where like this. Let's see. Yeah. So because insulation is more insulating, so it would be stretched out like this, like that, and then this insulation right here is also insulating, so this probably not that far. This insulation right here, that's not right. This insulation right here would also be thicker because it's more insulating. And then, anyway. So this entire measurement would be 24.99 right here. Anyway, I'm just that. So we're 0.17 deep into the wall in terms of R value. And then remember what I said about proportions? We're just going to divide it by the difference between these two temperatures. What's 97 minus 74?
Wait, what? What's
23.
97? Oh,
97 minus 74 is 23, yeah. Jeez. So, gosh.
Wait, how'd you get 23 real fast? You just did
97 and 74, minus 97 minus 74. So if you look right here, you have, remember the graph that I drew at the beginning of this? So this is 97 degrees and this is 74 degrees. We're essentially going to draw a line that goes from 97 degrees at the beginning of the wall, and it's going to drop all the way down to 74 degrees at the end of the wall. Now, this isn't going to be to scale, right? Because it's going to look more like, it's going to be steeper. It's going to look more like this, essentially. Okay, fine. It's going to look more like this. So see how like the temperature changes? It's not that much up here, but changes a lot in the insulation. You see here? Oh, that right there, that's the start of the insulation, that's the end of the insulation. Look how much temperature change there is right there. Right? So much temperature change. So I don't know what we're doing is we're just finding the points, these points, that point, this point, this point, that point, that point, that point, all throughout the wall. Did that make sense, or did that further confuse someone?
does this make sense?
Oh my god, it does. Come on, it has to make not sense. It has to not make sense to someone.
It's 100% making sense to me.
Yeah, I understand it.
Really? Oh my gosh. How? Okay. Cool. Right. So you see here this after the outside air film. Right now we're finding, might be hard to see. I'm going to zoom in even further. Right now so you see here, this is outside the air film. This is inside the air film. Right now we're trying to find how much this is right here. How much this is right there. How much that is. So it's literally just this 24.99 divided by 0.17. That's how long this is, and then we're just going to multiply it by 23 because that's this entire length right here, 23 degrees Fahrenheit, right? So we got this proportion right here. So we got this as a part of this, and then we're just going to multiply it by 23 to find out absolute value, or like the actual value is of this thickness. Does that make sense?
So from 97 to 74, the temperature change is 23, and then now we're trying to find the tiny change between each component.
Right.
Okay. And to do that, we multiply the components R value divided by the cumulative R value times 23.
Right.
Okay.
So remember, R value is like how deep we are into the the wall. So we're not that deep into the wall, but there's a lot more wall that's left. So that's essentially a percentage of what we got. And then we multiply that percentage of how far we are into the wall in terms of the R value times the temperature to like because they're directly proportional. So this right here, someone just put that into their calculator.
Yeah, I got 0.156.
0.156?
Yeah, I got the same thing.
All right, cool. 0.156. So what does that mean? What does that mean? That's the amount. That's how thick this bit is in terms of degrees. 0.156 degrees. 0.156 degrees right here. Compared, and then that's gonna be compared to like Wablamio, this whole 23 degrees Fahrenheit. So we only have that small 0.156 right there.
And that makes sense because it's like, okay, the outside air film is doing no work, essentially. Almost little to no work insulating.
Exactly.
Right.
So I'm just gonna.
So then for the next number, is it 0.57 divided by 24.99 again? We keep using the same cumulative value?
So we're going to use the same cumulative value because this value never changes, 24.99, it never changes, but we get deeper into the wall. So we're going to use the next cumulative R value. We're not going to use the component R values because that would assume, like, say we have our wall right here, right? So we have the air film, and then we have the brick, and we have the rest of the wall. Bleh. We'd be going this far into the wall because we're using a cumulative R value. If we instead used the face brick value, this component R value, we'd be only measuring this far, right? Now that doesn't look like a problem, right? Because we're ending at the same point, but because of the calculations we're doing, we're going to still start right here because of the way we're doing our calculations. So you see, you're supposed to use the cumulative R value because you're not going to get far. Like if you keep on going, like 0.157, boom, that's so far, right? Like, we're supposed to reach that point. But if you just use the 1, sure, if you start from here, then you're going to reach it. But you're actually starting from here, and you have so much more that you're supposed to go. So we're going to be using the cumulative R values. Sorry, we're just going to do 0.156. So now we're just going to do, oh gosh, my papers. All box. 0.8, okay. So now we're just going to be 0.57 divided by 24.99, and then multiply that by 23 degrees, and what do you get?
I got 0.5246.
I got the same as Molina.
Me too.
It is being weird. All right, then 23. You know what? I'm just gonna, jeez. You know what? I'm just gonna leave it. So you got equals. What did you say? 0.52. Something like that.
0.5246.
46, yeah.
Yeah, I don't know.
just
I
put
guess.
525.
525.
Yeah, I don't know
Alright,
how many decimal points, but yeah. I guess that many. That's good enough.
I'm just gonna resize this real quick so I have more to work with.
So now something I came across was that the vapor barrier and the air gap, or the air gap and the vapor barrier, are going to be the same, right? They have to be.
Yeah. So right here. This is going to be a little awkward. So 1 divided by, oh god, that's not right. 1.57 divided by 24.99 times 23 degrees. I know that's really hard to see, but can you guys read that right there?
Yeah.
Okay. So someone, what answer did you get?
So for that one, I got 1.444.
Yeah, me too. The same thing as Imran.
Cool. So now we're going to go to here, and we're going to remember we're going to use the cumulative R value right here. So it's again going to be 1.57 divided by 24.99 times 23 degrees. And you can see it's the same. Gosh, my navigation is off the charts. So you see it's the same value. So it's going to give you the same answer, 1.444. Yeah?
Yeah.
Cool. So now we're getting to slightly bigger numbers. So 9.07 divided by 24.99 times 23. What do you get?
8.34.
8.34.
Or,
Okay.
well, 8.35. My bad. Rounding.
35. Okay.
I have a question.
Yeah, shoot.
So for face brick, why does that say 0.17?
Ah, shucks. Yeah, that should be
Oh, okay. I was just
0.57.
making sure. Sorry.
That was my bad. I'm so sorry. What the frig? Yeah, that's supposed to be 0.57. Sorry. Hoping I didn't mess up anything else. Yeah, okay. I know it's sloppy, but we'll just move on. 9.69 divided by 24.99. What did you get? Times 23.
8.92.
8.92. So just a small thing to observe. You see how the component R value of the insulation board is 7.5. You see how big of a jump it was from the vapor barrier through the insulation board? See, that's like almost like 7 degrees. But here, this jump, because this number, 0.62, it's much smaller than 7.5 degrees. So the jump is smaller. Right
And
there.
again, this makes that common sense. Like, okay, the insulation board is, well, obviously insulating, but the plywood's not really insulating.
Yeah, so there's more of a temperature change because it can insulate better. It can take more heat. Cool, moving on. 9.69 divided by 24. That's literally the same thing. I'm just going to copy that. It's the same R value because the metal studs, it has an R value of 0. It didn't really add that much to the equation. Cool. Next, we have big boy numbers. 23.75 divided by 24.99 times 23 degrees. And what did you get?
21.85.
21.85. Leo, this is a small, I'm just gonna elongate. I'm just gonna give myself more room. So 24.31 divided by 24.99, that's not a point, times 23, what do you get?
$22.37.
2.37, we're almost there. 24.99 divided by 24.99 times 23, what should you get?
23.
23, beautiful. All right, now we just have to do a little bit more math. Just a little bit, it's not that much. It might be. So now we know the, all right, how did I go? Now we know this is, now we know all the relative temperatures. So this is 23. This measurement right here, this measurement right here, this little thickness right here is 0.16. This measurement right here, between these two, right here, is 0.52. This measurement, you get the idea. This measurement right here, it's after the air gap, it's 1.44. Right here, this much is 1.44. And then, you know, you make it all the way past the inside air film, and then you eventually add up to 23. But the temperature isn't anywhere close to 23 degrees. It's between 97 and 74. So what we're going to do is we're going to take this, we're going to take all these values, okay? We're going to take this value and subtract it from 97, because you see how the temperature is getting lower. So we're just going to take these values and then subtract these from 97. So what's 97 minus 0.156?
96.844.
Degrees Fahrenheit.
Oh, shit.
And this makes sense, hopefully. So you see how this thickness, if this thickness is 23 right here, this thickness right here is 23, and this thickness is 0.156. This thickness is 0.16. And this measurement right here, this line right here, is 97. We're obviously going to go down 0.16 degrees and reach 96.844 degrees Fahrenheit. Does that make sense?
Yes.
Okay. If it doesn't make sense, hopefully it'll make more sense once we go further down. What's 97 minus 0.525?
Wait, so now I got a real quick question. So
Yeah.
how come we keep using 97 and not the number before? Like, how come we don't use? Yeah, that's just a question.
Yeah. So remember this graph that I made, or this diagram that I made, right?
Mm-hmm.
I don't know if you can see the lines. I'm just gonna.
No, I can see him.
Beautiful. So remember when we were taking the using the cumulative R values, right? This is the cumulative R value. This is the cumulative R value. This is the cumulative R value. We're always starting from here. We're always starting from 97.
Yeah, you wouldn't start at the next component. That wouldn't make sense.
No.
I see. Okay, I got you.
Right. Okay. Did that make sense for everyone else? Did that not make sense?
Made sense to me, honey.
Cool. Okay. So we're going to take 97 and then we're going to subtract 0.525. What's 97 minus 0.525?
96.475.
0.475 degrees Fahrenheit. Now what's 97 minus 0.1444? Or 1.444. My bad.
95.555.
95.555 degrees Fahrenheit. So we should have written degrees Fahrenheit right here, but this is the actual readings that we're using now, so we have to write degrees Fahrenheit. So what's 9? Oh, it's the same thing because the cumulative R value didn't change, so the temperature change didn't change. I have 95.555 degrees Fahrenheit. Moving on, 97 minus 8.35. What do you get?
88.652.
652 degrees Fahrenheit. And what's 97 minus 89? 8.92.
88.082
degrees Fahrenheit.
88.082. Okay.
So the cumulative R value doesn't change. Therefore, temperature does not change. All right. Oh gosh. 97 minus 21.85.
75.141.
1. Beautiful. Degrees Fahrenheit. Second to last. 97 minus 22.37.
74.626
degrees Fahrenheit. Finally, what's 97 minus 23?
74, baby.
74 degrees Fahrenheit. So you see how like small temperature changes correlates to small R values. Big temperature changes right here. See that big boy jump? Correlates to large R values. Cool. So we're just gonna graph that. We're just gonna write this down, and then we're gonna go to this graph real quick. I'm just gonna redo that. I'm gonna get a bigger screenshot. Cool.
For homework purposes, do we need to plot it on the quote-unquote graph?
I would.
Okay.
Wait, what graph?
This wall drawing is right above the chart.
Oh, okay.
So I think it'll also like applying the graph. I'm not going to say you should. I'm not going to say that. I'm not telling you how to do your homework, but it is a useful visual representation of exactly the concept that we're going through or going over. So I'm just going to draw a few guidelines. We draw one right there, there, there. And this is just an approximation just to show you like the different slopes, and then I'll just do a quick conclusion after I do this. So this is going to be 97 degrees. Oh gosh, I'm going to write in black. 97 degrees Fahrenheit, 74 degrees Fahrenheit. Now 23, that's divided by 2, that's 24, 12, so this is going to be 86 degrees Fahrenheit. 80 degrees Fahrenheit. And then 92 degrees Fahrenheit. So we're going to try to keep it proportional, all right? So now we're going to plot some dots. I'm also going to draw a few more guidelines. One before, after. There. Here, I'm going to draw this
Those
in
are
black.
arbitrarily placed, right?
Arbitrarily placed. But they're almost to scale, so you can just get a sense of like a visual representation of exactly what this concept is. All right, so we have we have the air film, we have face brick, air gap, vapor barrier, insulation, plywood, bat insulation, and the stud, gypsum board, and oh, I forgot one more. Obviously, the inside air film. Right? So we're going to start plotting points. I think I'm going to just draw some more guidelines real quick. So this is going to be +3, so that's going to be 95. This is going to be 89, 83, and 77. Make this smaller. 77. Oh gosh. 83, 89, 90, 95. Right. So they're just smaller separations. So now we're going to plot these points. So we have the first point we have at 997, right? So that's, oh gosh, that's really zoomed in. So you have the reference point, it's 97. Now once we pass the outside air film, it's going to be at 96.844. So once we pass the air film, bam, this would be 96.44. Somewhere right there, maybe. This top bit isn't to scale. Draw that this is actually going to be 98. This is going to be our 97. This is going to be our 97. 97 degrees Fahrenheit. Right there. Right. All right, we're just going to plot these points. Just going to erase that. So 97 right at the edge of the air film. Once we get in past the air film, it's going to be at 96.84. That'll be about there, maybe a little higher. Once we get past the face brick, it's going to be at 96.48. About there. Once we get past the air gap, 95.56. Right about there. And we're just going to keep going down. Vapor barrier, 95.56. Just going to stay level. Insulation port, 88.65. 88.65, that's like about there. Plywood, 88.08. That's like around there. It says after bat insulation, it's going to be 75.14. Right, 75.14. down there. Gypsum board 74.63. Finally, inside air film 74. I'm just going to connect the dots. Bam, 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 straight, bam, bam, Lamio, bam, bam. And that's the graph you should get. At least that's the graph I got just by drawing it just now. So you can see there are different slopes to the line, right? You see how inside the insulation, the slope is much steeper. There's a lot more change in the temperature because it's an insulating material. See here, in this insulation right here, it also is pretty steep because it's the insulation is pretty high, you know? So it's just a visual representation of of how much the temperature changes inside the wall. Now, why is this important? Well, it's about dew points. So let's say the dew point. Now, this is from what I remember from the lecture. So let's say the dew point is 80 degrees Fahrenheit, right? That was dew point. Now, what is the dew point of 80 degrees Fahrenheit? It means that once the temperature reaches 80 degrees, water starts to condensate straight from the air from water vapor. The air reaches 100% saturation, right? So water will start condensating. Dew point is at 80 degrees Fahrenheit. That's right about here. Right? So if you see here, you see how the temperature goes past 80 degrees? So right at this point, right here, is when water will start to condensate inside your walls, and that's a problem, right? So how do you fight that? You would use a vapor barrier before it can reach the wall temperature can reach the dew point. So you see, we already installed a vapor barrier. See here, vapor barrier right there. So the dew point won't reach. So once the temperature reaches the dew point, it won't do that. So essentially what it's doing is right there, the dew point is still right there. Once the vapor barrier is there, it reaches the dew point that's on the inside. Let's say that's like, I don't know, 60. Say it's like 0 degrees Fahrenheit. No, 50 degrees Fahrenheit. Dew point. Right? Beautiful. Dew point is 50 degrees Fahrenheit. So it's more like, let's see. So it's more like this, I would think. So it starts at 80 degrees at the outside, and like dew point slightly drops. But once it reaches the vapor barrier, it goes whoop woof, way down. Dew point drops way down, and then reaches, let's say, this line right here is 50 degrees Fahrenheit. So it's an indication of where you should put your vapor barrier. Like if you didn't have a vapor barrier, then dew point would just consistently stay there. It'll probably like get to 50 degrees Fahrenheit. But what if the dew point wasn't 50 degrees Fahrenheit inside? What if it was also at 80 degrees? That's impossible. What if it was at like, I don't know. What if it was at 74 degrees Fahrenheit? It would like do something like that. But you know, maybe the dew point doesn't change like that. Maybe it doesn't. Maybe it's not a straight line. Maybe it's a super weird curve. So you see right there, that's not right. So you see there, the dew point would touch the temperature inside the wall, and then there would be a water problem, right? So the reason we do this is so we can decide where to put a vapor barrier, essentially. So I'm just gonna do one last thing. What if the dew point was 90 degrees Fahrenheit. Now it's slightly more dangerous. Starting dew point is going to be all the way up here, you see? And has a much higher chance because it's starting up. You see, all the way right there. It's already hitting the temperature right there. So we're going to install a water vapor barrier right there, just so we can alleviate the dew point right there. That's going to go straight down and then just probably something like that. But the reason we're doing this is so that we can, in a way, predict how where inside the wall there would be a water problem, so we can effectively treat that by installing a water vapor barrier, before the inside wall temperature reaches that dew point. Does that make sense?
We don't want no mold inside the house, is what the vapor barrier is doing.
Yeah. Does that not make sense to anyone?
The graph makes sense. Like, I understand the graph.
Okay, cool. Well, that's the homework. If anyone has any other questions, like, speak up, I guess. I'm done, I think, unless anyone has any questions.
I have a question.
Go for it.
On the chart, it says there's a row that says reference point. I think we used those points and label them on the wall section, right?
Yeah, you're supposed to use these points.
But yeah, but with the letter.
Oh,
Right.
this bit. Yeah.
Yeah, like, so the graph that Edison drew, like, I followed along, right? And I labeled it A, B, C, D, and so on and so forth.
Yeah. So.
But then, you know what? I do have a question. Now, once you get to the 2x4 stud and the bat insulation, it's like it doesn't go. That doesn't really apply, right? You can't have H and I be on the red line. Like, the red line can only include either point H or point I. Is that correct, Edison, or no?
Yeah. So for that part, I don't know. I think a
Okay, you're
lot
good.
of people don't know.
Don't worry.
So it's gonna be like D, E, F, G, and then I just jumped straight to I. I didn't even write in J. I mean,
You mean H?
H,
Yeah.
J, K, and then L is the temperature right here, and then
Yeah.
A is the temperature out here. So
Yeah,
yeah, that's the
That's what I got. So yeah, you know what? I'll just leave H out because I was confused. I'm like, do I write the H or do I write the I? That's the one part where I was like, I don't know what to do.
yeah.
But
Does that make sense to everyone? Cool. Any other questions? Anything I missed? Anything I could do wrong?
I have a question.
Go for it.
Could you explain why so on the component R, in that row, could you explain why you multiplied 6.25% by the 0 for the metal studs and then the 93.75% by the 15?
Yeah. So this was just like this was just a way that I could figure. So on the, how do I put this? On the homework, it says, hint, use the weighted average to calculate. Use common sense to see if your answer makes sense. So you're, like, remember what we did here? The R value changes inside the wall, depending on where you cut it. So the R value would be lower here because you're cutting through the stud, and it would be higher here because you're cutting through the insulation. This was the only way I could see it, like, because that insulation makes up 93.75% of the wall and metal studs make up 6.25% of the wall. So I was thinking just multiplying the component R value by how much percentage it takes up the wall would hopefully, like, find the average R value of this entire section, because these are two different materials. but it's in one plane. If we could consolidate the two materials into one R value by like adding up the two different R values, then maybe we would get a more accurate answer. Does that kind of make sense, or no?
Yes, it does. Thank you.
Oh my God, nice, cool. Okay. Any other questions? No? All right, beautiful. I'm going to stop the recording